Hi, in this video I will talk about Vision Transformer. Transformer architecture was first proposed for NLP domain. In the paper, attention is all you need. For an NLP task, transformer is an encoder-decoder mechanism. Encoder is the left part, and decoder is the right part. Note that in transformer architecture, convolution is not used at all. After the success in NLP, transformer architecture is adapted for image recognition as Vision Transformer. In this paper, only encoder part is used in Vision Transformer. This time, layer normalization is applied before multi-head attention and MLP. Transformer encoder is a stack of L encoder layers. Default value of L is 12. Vision Transformer is obtained adding a classification head to transformer encoder. Vision Transformer input is a set of embedding vectors. As the first step, input image is converted to a set of embedding vectors. Extracting embedding vectors from input image. Let this be our input image. As the first step, image is divided into patches. A patch is a square with edge length r. Default value of r is 16. C is number of channels. D hidden is the latent vector size inside Vision Transformer. Patches are processed in raster scan order. Then patches are flattened. These 1D vectors are transformed linearly to patch embeddings using a dense layer with no activation. A more practical method is to use convolution. Number of output channels is D hidden. Kernel size and strides are equal to patch size. This way, kernel overlaps with image patches. A class token is prepended to patch embeddings. Class token is learnable and has the same size with a patch embedding. Class token is not about a specific image patch. At the output of encoder, the vector at the position of class token becomes a representation of the whole image. Position embeddings are added to patch embeddings. Position embeddings are learned from scratch. The reason why position embeddings are necessary will become clear in later sections. Result is the set of input embeddings that are fed to Vision transformer. Dropout is applied after this summation. Before multi-head attention, let's inspect its building block self-attention. Self-attention interprets the relation between input vectors to get an idea about the context. Specific version used in transformer is called scaled dot product attention, and it is described in Attention is All You Need paper. Multiple self-attention blocks are used in parallel and called multi-head attention. Input and output of self-attention have the same number of vectors. For each input vector alpha I, a query, a key, and a value vector are computed. Query, key, and value vectors are linear projections of alpha I. A linear projection is implemented using a dense layer with no bias and no activation function. WQ, WK, and WV are weight matrices of dense layers. Query, key, and value terms are used in information retrieval systems. Let's say you look for a file inside a set of files. Query is how you describe the file you are looking for. Each file in the set is attached with a description which is key. Content of each file is its value. So, query is compared with the keys of all files. Result is a relevance or similarity score for each file in the set. Inside self-attention, value can be thought of as information content extracted from input. Query of each input vector is compared with the keys of all input vectors to find out which is similar at which degree. Dot product is used as the similarity metric. To compute each dot product, query and key vectors should have the same dimension dk. Value vectors may have different dimension dv. In softmax input, if one logit is very high compared to others, then softmax output resembles a one-hot vector. If high output corresponds to ground truth class, loss and gradient become very close to zero. So magnitudes of dot products should be kept low. If components of query and key vectors are independent random variables with mean 0 and variance 1, then dot product of a query and a key vector has mean 0 and variance dk. Dot product is scaled by 1 over square root dk to keep the variance at 1. Each row holds the scaled dot products of the query vector of one input with the keys of all inputs. Optionally, if some entries of this matrix shouldn't be included in the process, They are masked by setting them to negative infinity. Because inside softmax, e to the power negative infinity is 0. This is the case in transformer decoder for NLP applications. Applying softmax to each row separately, attention weights for each input are obtained. Sum of each row is 1. So attention weights are not fixed or learned, they are computed for each input. As the last step, each output is computed as a linear combination of value vectors weighted by attention weights. Output vectors have the same dimension with value vectors. As similarity indicated by scaled dot product increases, corresponding attention weight increases. Contribution of a value vector to an output vector increases as corresponding attention weight increases. Similarity increases attention, and attention brings higher contribution. Using all input vectors and adjusting their contribution, self-attention is aware of the context described by the set of input vectors. While combining value vectors for one output, value vector of corresponding input moves towards value vectors of other inputs. This is the effect of contextual information. One thing to note is that order of input vectors is not important for self-attention, it is permutation equivariant. If order of input vectors change, order of output vectors change the same way. That's why positional embeddings are added while preparing input embeddings for transformer. Self-attention is the core of transformer. Thanks to self-attention, transformer can process different types of data, text, image, etc., as long as input is represented as a set of vectors. Multi-head attention. Multi-head attention is the parallel application of multiple self-attention blocks. Query, key, and value vectors are computed. Each self-attention block, attention head, works on different projected versions of query, key, and value vectors. Query, key, and value vectors are projected using dense layers with no activation. Dimensions of query, key, and value vectors are reduced. These are the weight matrices, and H is attention head ID. In attention is all unit paper, these are defined as linear transformations and no bias is used. In some implementations, these projections are applied with bias as affine transformations. Attention head works on projected vectors. Sequential linear layers can be represented as a single linear layer. For query vectors, for key vectors, and for value vectors. This is attention head 0. Other attention heads are added in parallel. Outputs are concatenated. And one final transform is applied. Here capital H is the number of attention heads. Default value is 12 for vision transformer. And dimension of value vector is equal to d hidden divided by capital H. Because in transformer architecture, input and output of multi-head attention should have the same shape because of residual connection. Multilayer perceptron, MLP. MLP has two dense layers. Activation of hidden layer is Gaussian error linear unit. Vector size is expanded by 4 in hidden layer. Dropout is applied after dense layers to avoid overfitting. Classification head. Vision transformer is trained in 2 stages as pre-training on a large dataset and fine-tuning. Classification head for pre-training is an MLP with 1 hidden layer. Penultimate layer produces prelogits. And output layer produces class logits. For fine-tuning, pre-trained head is removed, and zero initialized single linear layer is attached as classification head. Linear layer produces class logits. Comparison of CNN and vision transformer. Reaching general rules from specific observations is called inductive reasoning. Similar to inductive reasoning, an image classifier learns to create a mapping based on observations or batches of training data. Inductive bias is the design choice or assumption that narrows down the set of solutions during the search for a mapping. Let this be our solution space and constraint solution space. Smaller solution space might be advantageous if amount of training data is small. The downside is that better solutions might exist outside constraint solution space. In CNN, a kernel processes pixels in its receptive field, only a small 2D neighborhood of center pixel. Same kernel weights and bias are shared over the image. In vision transformer, only MLP layers are local and translationally equivariant. Self-attention layers are global. 2D neighborhood structure is used while cutting the image into 2D patches and interpolating pre-trained position embeddings if image resolution is higher at fine-tuning. CNN generalizes well on small datasets thanks to convolutional inductive bias. With less inductive bias implying a broader solution space, Vision Transformer requires large datasets to outperform CNN. That's all for this video. See you next time.